Okay, I think we're recording, so let's dive in. All right, everybody. So we're into our next notebook for the series, and we've got first part of two. Today, we're going to be taking a look at big O notation, or the mathematical term would be asymptotic notation. I'll introduce you to the root of the word asymptote. We'll have a look at that, and then have a look at asymptotic complexity, and then some terms that we can use to measure asymptotic complexity. That encompasses both runtime and also space in terms of memory allocation. We've had a little look at memory allocation with NumPy, and had a good contrast between the NumPy array and linked list. So in this lecture, we'll see how that can be measured in terms of mathematical notation. And then we'll also apply that to have a look at searching and sorting algorithms. We're going to have a look at the second part, so that's going to be 06. All right, so we'll show you some examples of these runtime classifications, and then we'll go on to explore those and apply those in 06. Okay, so let's just introduce you to this word that we call asymptotic behavior, and let's start with an asymptote. So that is a fancy word, that's a mathematical term that we use for a line. It could be a straight line, it could be a curved line that is mapped against a graph of a function. So if you think back to GCSE maths, A-level maths, when you're drawing a graph, f of x, let's show you an example here. Here we go, f of x equals 1 over x. That would be, you'd plug in some values for x, and then you get back the y values. So it gives you x and y, you can plot those. Okay, that would give you a graph that looks like this. Okay, you might have some other graphs as well, graph of functions, f of x, f for function, and then it gives you the x and y values, plot them on a 2D plane. Okay, so an asymptote, essentially, here is modelled as a straight line that comes fairly close to the curve of a function, but never quite touches it. And that will go on till infinity. The numbers will just get smaller and smaller and smaller as the number of floating points gets larger and larger and larger. It gets very, very close, but never quite touches it. But of course, when you view it in a sort of graphical format, it looks as if it's fairly close, doesn't it? As you can see there. It's sort of quite close, especially on that one, it's very close, isn't it? On those asymptotes, but not quite touching it. Doesn't quite get there, okay? So that's where the root of the word comes from, asymptote. And that gives us this approximation for the eventual destination of our function. And of course, remember, the idea here is that we're trying to measure the performance of functions, of algorithms, essentially. So that maps quite well to the mathematical display of a function, of a graph that we're used to seeing in maths. We'd see these, wouldn't we? You know, think back to things like the sine curve, the cosine curve. You have a quadratic equation. We can plot that on a 2D plane in maths, and we're going to transfer that concept to programming and computer science, so that gives us a way to approximate or to classify functions, and that's essentially what we're going to get to, algorithms, what we're going to get to. Okay, so these asymptotes, usually straight lines, could be curved lines as well, depending on the nature of the curve, the number of parts that the quadratic equation might have. But here, as you can see, for this one, 1 over x, the numbers are just going to keep getting smaller and smaller because it's 1 divided by x. So whatever x is, whether that's 5 million, it'll be 0.00000 all the way up until infinity. Okay, so that's what an asymptote is. Let's tell you about asymptotic notation. Oh, here we go. Here's just the quadratic version of it. So if you've got many parts to it, x cubed plus 2x divided by 4x squared minus 1, you get these, all kinds of funny lines of different shapes, and that gives you the asymptote drawn across there. Okay, so it gives you a way to approximate the graph of a function. Okay, but when we talk about asymptotic notation, remember the root word of asymptote is a straight line. Asymptotic notation is interested in measuring the rate of growth. So how does this function, this algorithm that we're dealing with in programming, how does that scale as our value of n, translate that from x, a value of n, the number of elements in our data structure, the number of operations we're performing in an algorithm, how does that scale as n grows? Okay, that's what we're interested in, and that's where big O notation comes in. Has anyone heard of big O notation or measured it before? Yeah, okay. All right, okay, well, don't worry, I'll tell you all about it. But it's good that one of you has heard of it, so that's good. Okay, so we're going to map that mathematical concept to our algorithms, okay, to measure the rate of growth. Because to think about it in simple terms, you know, we could easily run a sorting algorithm on an array of 50 elements. It won't take the program very long to sort through an array of 50 elements. But what happens then when that scales to 50 million, 5 billion, 5 trillion? Think of big data out there. You have huge amounts of data, huge, absolutely colossal, petabytes, even bigger than that, amounts of data to sift through, to search through. Okay, that's also what we're going to look at, searching and sorting. So rather than focusing necessarily on time, because time's always going to vary depending on the state of the structure, the environment, the hardware, the architecture you have available, we're more interested in more constant classifications. How do we measure in terms of rate of growth mathematically? How do we measure that in a sort of more stable mathematical, theoretical classification? That's what we're going to try and do. We're going to try and classify how these algorithms grow. Okay, and that's where we get to big O notation. Okay, big O notation. And we've actually got other Greek symbols as well. So big O, the more famous of them, probably because it describes the upper bound, or the asymptotic upper bound. Yes, come in. Asymptotic upper bound. And so we're talking about upper bound, lower bound, and sort of average case, or asymptotically tight bounds. So that maps fairly well to sort of worst case, best case, and average case. Or sometimes, there is always going to be the same amount of growth because of how the algorithm's coded. Okay, that's never going to change because of how it's described. So it could run exactly the same way, irrespective of the value of n. Okay, but of course n will affect it. Likewise, the state of the data structure for these other two. So big O describes the upper bound. It's not going to be worse than. It's not going to be any more than a particular classification, O of n, order of n. It's proportional to the number of elements in our data structure. That's linear time. Okay. And let me just, if that was a quadratic equation, what would that look like? Here we go. So here's f of n. Think f of x. Here's f of n function, number of elements we pass in. You might get performance that's a little bit like this. Okay, that's our sort of worst case. If it was in completely unsorted structure, conditions were such that we needed to do a lot of operations on it, that's our sort of worst case. That's the upper bound that it could be, okay, against the average running time. All right, so that's big O, written as O, and then a value, n, for number of elements, okay, or omicron in Greek. I'll show you the Greek symbols in a minute. Okay, O for omicron in Greek. But we have other Greek symbols here. Omega, that's this little horseshoe style symbol that we have. Okay, that's the opposite. That's the lower bound. So that's like the best case. It's going to be at least this. It's the best case it could be. So if conditions are all in our favour and it's nearly sorted, or the item we're searching for is near the start of our data structure, we're going to find it quickly. We're going to find it more quicker than average, faster than average. Okay, so that's the lower bound if we plotted that out, okay, in terms of finding something. All right, best case in one sense. It's sort of the best case scenario. So big omicron, O for omicron, and big omega, that's our one that we see here, the horseshoe style shape. And then the one in the middle is where they're asymptotically tight bounds. They're basically the same, precisely at the same rate, exactly at that point. It's going to grow exactly proportional. That's straight in the middle. Okay, that's our sort of middle bound here, where they're exactly the same, the constant in one sense. Okay, so we're trying to find words and symbols that we can describe performances of our algorithms and our data structures based upon variables, because they're always going to change, aren't they? Depending on the state of the data structure, the type of operation, the nature of the operation that we're performing. Okay, so these are just symbols, sort of older variable names, if you like. Don't think of it as being more fancy than it is. These are literally just Greek mathematical symbols that we apply to these types of operations. They date way back. You've probably seen the sort of E shape for sum, haven't you? Sigma for sum, back in the ancient Greek times, okay? You'll probably be familiar with a few of these. Alpha, beta, gamma. Delta as the sort of triangle shape, okay? We've just seen theta. There we go, that's our That's our asymptotically tight bounds. That's big theta here. Okay. O for Omicron, that's big O. And then we had omega, didn't we, for the best case. All right, so that's really where these symbols come in. They're just old variable names, if you think. We're used to writing English letters, A, B, C, D, X, Y, Z. Okay, these what ancient Greek mathematicians would have done. They would have used these symbols, their language at the time. Okay, so don't think of it as being more fancy than it is. These are just ancient terms that are applied and still applied today. Okay, so that's why I wanted to show you them. All right, so just in case you see those symbols, you know what they refer to, okay? But you're probably more likely to encounter big O, especially as you're just getting started. As we get more precise and when you get more interested in comparing the differences between those bounds, you might start to see those other symbols too. Okay, so just wanted to show you that. Yeah, let's talk about some of the common runtimes, and this is a bit more familiar territory now. We're starting to see this. So O of 1. If we see this, O of 1, constant, you know, in general terms, if something is constant, it never changes. Exactly, it's always going to be the same, isn't it? And can we think of a sort of typical operation where the time taken or the performance is never going to change with respect to the size of the data structure, the state of the data structure? Has anyone got any ideas as to what is always a constant operation? Anyone? Okay. Well, remember we spent a bit of time thinking about indexed data structures. Yeah, so cast your mind back to Python lists, NumPy arrays. When we type in the index position, we can go straight to it, can't we? We don't have to sort of iterate like a linked list. We have to sort of start at the head of the list and iterate our way through to get to a particular item. That's a different type of classification. We'll come to that. But for now, just focus on the indexes. We can go straight there, can't we? So it doesn't matter whether we want to get to position 0, we want to get to position 9,999,999. We can go straight there in the same amount of time. So it's always going to be constant. It doesn't change based on the size of the data structure. It doesn't matter if you've got 50 index positions or 5 billion index positions. We can always go there because we know the index position. Hey, come on. Okay, so that's what we would call constant. It doesn't change, or it shouldn't change, or at least mathematically it would be the same operation. It's going to fluctuate based on hardware, based on which environment you're in, okay, fine, but mathematically, our sort of stable classifications, it's going to be a constant operation, okay? And we'll contrast, like, calculating time, the amount of tangible time it takes to do something on a hardware versus the number of operations. So you get to see the difference between them. Okay, so that's constant. Let's talk about linear, because I've just briefly touched on it, didn't I? So think back to linked lists. What did we do with our linked lists? We had a pointer to the head and the tail, but if we wanted to work our way through the list, we had to let's start at the first element. To get to the next one, we have to look at which pointer. What does the head of the list do? It's got a particular attribute that does something. It holds a memory address to the next element. Yeah, so next element. So it points to the next element. So if you want to get to the sequential element, you have to iterate, don't you? You have to iterate. So for, or while we're not at the end of the list, keep repeating. So that's essentially linear. If we had to get to the end of the list, we've got to iterate n times to get to the end of the list, haven't we? If we've got no tail pointer, if it's a singly linked list, we've got to iterate to get there. It's not indexed. We can't go straight to the end of the list, or position 7 or position 5, position 10, because we don't have the index position to get there. So if we start from the head of the list, we've got to iterate n times to get to it. So that's linear. So therefore, time taken is proportional to the size of n, number of elements. Yeah. So a list of 5 elements, a list of 50 elements, a list of 500 elements, it's going to take the amount of time dependent upon how many elements there are to find what you want. And of course, best case, it's near the start. Worst case, it's near the end. Average case, somewhere in the middle. Okay? So there's a good contrast there between constant and linear. Has anybody come across logarithms before? done A-level maths, or is it maybe it comes up at GCSE maths? I can't remember whether it does or not. But logarithms, Raja nodding, Tyler nodding. Okay, so anyone want to try and put into words to define what a logarithm is? Can be a tricky one to put into words, can't it? Anyone come across it? Log base 2? You might have seen that on your scientific calculator maybe. Log base 2 of a value. You've probably seen it, you just haven't done it recently. Yeah, so it's fine. So logarithmic behaviour, essentially, we've got an example on it later, so you'll get to sort of see a tangible, concrete example. But essentially, you're trying to find the power that you need to essentially multiply your exponent by to get to n, essentially. So if you give log base 2 of n, you're going to get back the power, the number that you raise a number to, okay, to get something. So if you do log base 2 of 8, you're going to get back 3. Oh, very good. Yeah, you're going to get back 3, aren't you? So it's 2 times 2 times 2. 2 to the power of 3, 2 cubed. Okay, 2 times 2, 4 times 2, 8. Gives you 8, yeah? The idea being is that you can, it grows much slower, the power that you raise by grows much slower as n increases. So actually the curve is much leaner. It doesn't curve, and I'll show you the curve in just a minute. It doesn't grow anywhere near as fast because you can get to really large numbers, you know, thousands and millions, and actually the value returned, log base 2, is actually quite small, which is great because essentially what we're doing is we're dividing in half every time. That's the basis of logarithms, okay? So we can actually, this is applied in binary search, we're going to see this, okay? Enables us to find things much faster than it would do if we're using linear time. If we had to iterate for every single element, it grows much faster. Okay, so it allows us to find things in faster time. Right, so then to put this one together, linear rhythmic is like the blend of logarithmic and linear. What do? You take linear, O of n, and you multiply it by O of log n to get O of n log n, okay? So it's really just logarithmic behavior done n times. And that would be the principle of merge sorts or quick sorts, which you're going to see. Okay, so it's really, once you understand those two, you just do them both together. Okay, it's logarithmic principles done n times. All right, and then let's build on that with quadratic. O of n squared. I've just said it with the logarithmic behavior. O of n squared could also read as O of n times O of n. Yeah, so if we said that O of n is one loop, essentially, iterate for the number of elements in a structure, if that's one loop, what would O of n squared be? Another loop? Yeah, oh, another loop inside that loop. It gives us, because O of n times O of n, remember we said O of n is broadly equivalent to iterating through the entire structure. We do it n times, do an operation n times to kind of get through to the entire structure. If you want to print every element in your list, in your array, you've got to write a for loop, haven't you? So for each element in my for loop, print something out. So read that as O of n, because you're saying I've got to do something. I've got to do an operation for all of my data structure. And how many elements have I got to do? Well, that depends on n, doesn't it? Number of elements, n for the number of elements, okay? So what quadratic would read as is O of n times O of n. You've got a for loop inside a for loop. So if you've ever seen a nested for loop where it says for, I in your data structure and then for j in something, that essentially is a 2D an array. So for every row, do it multiple times. Okay, that would be O of n squared, wouldn't it? A for loop inside a for loop. All right. So you're going to see that with some of our algorithms. I don't know if you've ever come across bubble sorts at all. Has anybody ever done bubble sorts? No? Roger, have you done bubble sorts? Yeah, okay, all right. Well, you'll see a for loop inside a for loop. And that's O of n squared. Okay, all right, almost there. And then two others. Okay, so these are kind of these grow very fast, and we kind of want to avoid these. We really want to avoid quadratic, if we're honest, and you're going to see exactly why in just a moment as we plot it. Okay, exponential O of n, O of 2 of n, so that n becomes the power. So as that grows, that scales very fast, doesn't it? Because to the power of 2, 5 to the power of 2, 5 times 5, 25, yeah, not too bad. But what about 5 to the power of 3? I think that's 25 times 5, 125. So the rate of growth from 25 to 125 plus 100 for an increase of 1 from 2 to 3. And then it goes much steeper from there, doesn't it? 125 to the power of 5, it just goes up very steeply, okay? And then factorial, if you don't know, that's basically n times n minus 1 times n minus 2 times n minus 3 down to 0. So 5 times 4 times 3 times 2 times 1, and then 6 factorial, 6 times 5 times 4 times 3 times 1. And so it grows again incredibly fast. So let me plot those on a graph just to make it visually easier for you to understand. And then we talked about constant, O of 1. Constant never changes. You guys told me that, yeah? So essentially it doesn't matter what the size of n is. By the way, n is elements on the x-axis here. So n of 0, n of a million, let's say, or something like that. Something very big at the far end. And then operations, we'll read that as time, the number of operations that we're going to perform, versus the number of elements, which is n. Okay, so constant never changes. Never changes. Doesn't matter if you've got 5 elements or you've got 5 billion elements. It's always going to be the same. Never changes, irrespective of n, okay? Log n is the next, well, a constant is virtually impossible to achieve. Well, not in our real world, tangible world, but you're only going to do it with certain operations. But in talking about searching and sorting, finding typical operations, we're only going to have, we're not going to be able to achieve that. But for log n, that scales, as I said, log base 2, that scales very slowly, which is helpful, isn't it? That scales very slowly. Like we said, log base 2 of 8 gives us 3. And then I think the next one up is, there's several in between. I can't remember what they were. I think if we take something like 4,096, I think that gives us 12. Nice round number for log base 2 of 4,000. So 3 for 8 to 12 for 4,000. That's like plus 4,000. And the rate of growth is what, plus 9. So as you can see, it scales incredibly slowly. As you can see, it's that kind of green, you can just about see it, it's that green line there. So that is much better for larger numbers of n. It scales much slower. It means we can do things much faster, okay? We've got O of n. Do you remember what we called that? O of n? Otherwise known as? Linear, well done, Marilyn. Yeah, linear time. It's linear. The time taken is linear. It's proportional to n, isn't it? So it's the same number of operations, and usually constant operations, like if you're printing out an array, printing out a linked list, it's usually going to take the same amount of time to do that, to look at one memory address, print out the value, look at another memory address, print out the value. The time taken to do that doesn't change. You've just got to do it n times. Length of your array, length of your list, okay? So that's just proportional scaling. N log n, remember that's O of n linear times logarithmic. O of log n gives you O of n log n. Take those two, multiply them together. That scales a little bit faster. Remember, this is a small number of n, and that's a large number of n. So it's starting to scale a little bit, okay? A little bit, but not disastrous, and that's usually a good time to aim for if you're sorting. It's usually pretty good. Some algorithms you can do a little bit faster than n log n, but you need to have certain conditions to achieve that. So that's usually sort of a good standard to aim for sorting. Searching, if we've got a sorted list, depends on the conditions, got a sorted list, we can usually do that in log n. If you've got a sorted list, you might not have a sorted list. Okay, and if you don't, you'd have to then sort it first to get a sorted list. So you have to add those runtimes together. Okay, but these are sort of the good and fair. If you look at the, I know it says it's bad, but I think it's usually a pretty good standard to aim for. You'd have to get into serious size of n for that to start becoming bad. It's usually pretty good up until then. Okay, but really, as I said, we want to avoid this side, the kind of red area, the danger zone, and that's O of n times log n. O of n squared, which is n times n. As you can see, there's O of n, but there's O of n squared. So that scales much faster. It grows at a much faster rate than O of n for the size of our structure. Okay, and then definitely want to avoid O to 2 to the power of n and then factorial. So definitely want to avoid those two. Okay. So I hope that kind of plots it in visual terms for you. And the idea of me telling you about this and showing you this is that we want to get good at classifying algorithms that we run, functions that we perform, and also the data structures that we use. This is part of our whole idea here, that we're all about this. This is what we're all about, this module, is to get good at working out which algorithms are going to be useful for our circumstances. Hey, come on in. All right, so we want to get good at trying to recognize whether our algorithm is going to scale well or not. And that's entirely dependent upon how we code it. So it's in our hands, it's in our power. We can change that. Okay, so we will be referencing back to this quite a lot, so don't worry, it's not a one-time deal. We'll come back to it, and the idea is to train you to recognize how to classify your algorithms. Okay, and indeed that plays to your assignment, by the way, so that's what we're all about here in this module. And very useful for interviews, by the way. This is another motive for me telling you about this, because if you go for those big tech interviews at big companies, they will definitely ask you to classify algorithms. It's part of the kind of base standard that they look for in candidates, okay? So really good that you get used to doing this. Okay, so let me just tell you a bit about the variability. All right, this is our next slide. Okay, so we will be timing these operations just so you can get a concrete measure, so it hopefully kind of convinces you of the mathematical classifications. I'll give you some tangible number of seconds that it takes to perform things. But the thing is, that's always going to vary because it depends what architecture you have. I'm on a Mac, it's got an M1 chip, it's reasonably fast. You might be on an M4 chip, or you might have the most fancy graphics card that can do it even faster. You might be in a different environment to me, Visual Studio Code. You might have coded it in a different environment and got different architecture. So the process and different processes. So it's always going to vary depending on who's running the algorithm and what servers you have and what processing machines you have. Okay, so it's going to vary, the time taken. It also depends on the condition of the data structure. As we said, whether it's what extent it's sorted. It could be completely unsorted. It might be sort of half sorted. You might have a load of duplicates in there. Remember, messy data sets, you know, there's all kinds of different states and conditions you find them in. It might be completely unsorted in the wrong way. It might be sorted in the reverse order. So you then have to sort it into the correct order. Reverse around, whether it's highest to lowest, lowest to highest, alphabetical A to Z, Z to A. Okay, you might have to do completely the reverse of it to get it into order. Okay, as we said, the number of elements, and of course the actual complexity of the algorithm itself. And that's down to us. We can have some control over that in terms of how we code. Okay, so this is a good chance for you to recognize how you code, how you can get more efficient with coding. Maybe there's loops that you don't need to declare. Maybe there's variables you don't need to declare. You can make some savings on how you code as you get more efficient. Okay, so that's a good thing for you to develop, is get more efficient and refactor your algorithms so that they don't use up more than necessary space and time. Okay, so a good thing for you to go on to. All right. We talked a bit about this, didn't we? The best, average, and worst case. Remember, we mapped essentially the worst case to big O, best case to big omega, and then average sort of where this is going to be. Well, it doesn't quite map to average case, but it does map to where the algorithm is going to perform exactly the same way every single time. Okay, but we could apply this principle essentially of best case. Let's imagine that we are searching for an element. Okay, so we've got a list of elements. And we're just going to iterate through them. Imagine a linked list, for example, and we don't know where it is in the list. We start at the head of the list and we've got to work our way through. Where is it? And we stop when we find it. Okay, once we found that node, return it. We found it. Okay, so the best case is that the element we're looking for is going to be at the start of the list, because we only have to iterate a few times to find it. We don't then have to iterate the rest of the list because we've already found the element, haven't we? Yeah. So that's best case. It's near the start of where we look for. We only have to iterate a few times. Flip that round. Worst case, we have to iterate all the way to the end of the list to then find it. So we've gone through the entire list to get to it. Okay, that's worst case. Best and worst case, yeah? Average case, well, it's somewhere in the middle. Okay, we have to iterate a few times, from either end to get to where it is, roughly in the middle. It might be, in the middle quartile of that interquartile range. Okay, so that's general cases that we use to describe. Okay, we can't always say that it's going to perform the best case every single time because it may not. Okay, so we can't always give one single classification. So what you generally see is these three cases. In best case, it performs like this. Worst case, it could be this. In average case, it tends to equal out to be another classification. Okay, so those are some of the terms we're going to describe our algorithms and how they perform. Okay, it's not you can't just label it as being O of n, because it may not always be O of n. Some cases it will, some cases it won't. Okay, it depends on the type of algorithm that we have. Okay, so, let's talk about how do you find it out. Okay, so if you've not done it before, if you've not looked at a piece of code and tried to classify it, and remember classification, we're talking about categories. We're trying to categorize as linear. Is it constant time? Is it quadratic time? Is it linear arithmetic time? So, it's going to be hard when you start out, but trust me, it does get easier. And that's what we're trying to do with this module, get you used to that, okay? So let's look at some points here. This is some content courtesy of Gail Lakeman McDowell, written a great book, by the way, if you are going for coding interviews and you come up against these coding challenges, which you get set if you go for some jobs. This is a great book to read, by the way. And indeed, I'll be covering quite a lot of stuff from that. This is sort of the base standard that they expect. Okay, so first point she mentions is different steps in an algorithm essentially get added together. So let's take a very simple function. Okay, very simple function. Here we go, Python. We call two functions from that function. Okay, so we could say, assuming they're doing different things, assuming they're doing different operations, well, if this is operation A and this is operation B, essentially the summation, the performance of this function is going to be performance of O of A, operation A, plus operation B. Two operations, time it takes to do them, add them together. So we could say the performance is O of A plus B, or not O of A B, because that's A multiplied by B, but O of A plus B. The time it takes to do A plus the time it takes to do B. Okay, that's a very simple function. It gets a little bit more complicated than that, so let's move on. Okay, let's talk about the next point, which is dropping the constants. Okay, let's have a look at this. So let's imagine that we've got this function here. Let me zoom in so you can see it. Let's find both the minimum value in the list and the maximum value of the list. So here we go. We've got a for loop. For I in L, read that for every element in L, list, L for list. We could say n there. It's just an alias. Okay, so every element, every n in list, do a function. Okay, so that's linear time. It's directly proportional to the number of elements that we have in our list, whatever that is, okay, O of n. And then we do the same again, so for every element in list, same list, O of n again. So, is that O of n squared or O of n? We've got two loops, but which one of the two is it? Or is it something else? Is it O of n multiplied by O of n? O of n plus O of n, O of 2n? Any thoughts? Silence. Oh, okay. All right, this is new to you. Okay, fair enough. It's all right. We're getting used to it. So, for it to be O of n squared, we would have to have a loop inside of another loop, wouldn't we? Because in order to multiply them together, we would have to do every n, look at every list element, n times. So for each element in n, we then got to go through the loop again. That gives us O of n times O of n squared. So it's not O of n squared, but the point here is that you could think that it's O of 2n, because we've got 2 times linear time. So you could say, well, doing O of n twice, so why shouldn't it be O of 2n? Or O of n plus O of n gives us O of 2 of n. Why isn't it that? Well, remember we're trying to classify this, and we're really just looking for which category it is. Is it linear or is it quadratic? Well, it's more closer to linear, isn't it? It's O of n. We can therefore drop the constants. That's our bullet point here. We can drop the constant here. Okay, we only need to focus on linear time. Doesn't matter if it's 2 times linear time, 3 times linear time, half times linear time. Okay, it only needs to be classified as O of n. Okay, the exact runtime, I suppose you could argue, yes, is O of 2 of n if you do it, go through the loop every single time that you run the algorithm. But really, it just needs to be linear. So O of n. It's definitely O of n and definitely not O of n times n. That's the one thing we need to highlight here. Okay, it's definitely not O of n squared. All right, so that's one thing you can get simpler at, because remember, it's these categories. Let me show you them again. It's these classifications, you know, think data. We're not on a continuous range here. And others on data science and AI tracks, okay? You're used to continuous data and categorical data, okay? We're interested in these categories. We want to find which one of these it is, okay? And we've got to then just classify which one is it more likely to be. And it was more likely to be linear, okay? All right, let's keep moving. Let's look at the third point. So from here, different inputs. So be aware of different inputs that are treated independently. Okay, let's have a look at this example bit of code. All right, so we've got 2 lists. List A, L underscore A, and list underscore B. 2 different lists. Could we assume they're the same size? They have the same number of n in them. Is that a good assumption to make? Manish's shaking his head. It's probably not a good assumption to make, is it? There might be different sizes. Okay, if we have a single list, we know the size of it. It's going to be n, isn't it? Yeah, it depends on what the size is. But we've got 2 different lists. It would be quite dangerous to assume they're exactly the same size. In fact, it's more likely they're not going to be the same size. Okay, if they were, that's fine. We can have a single loop counter to do both of the loops. Do n twice, you know, n times n. O of n squared. Okay, but we've got 2 different loops, 2 different sizes. Therefore, we might have 2 different loop counters that are different. They're going to do a different number of times. A and B for each A in L of A. That's just one counter. And then another counter for the length of B. So therefore, we have O of A and O of B. What does that give us? O of A times B. Or O of A times O of B. Compress it. O of A times B, O of AB, okay? Because if these were the same size, we'd have n and n, that would be O of n times O of n squared. Okay, so here they're different counters, different variables, different sizes of n. We have different variables to, different counters to map to the size of each list. Therefore, it's O of A times O of B, O of AB, okay? And then what we're looking to, we're just looking to see where they intersect, so where they share the same values. If A is equal to B, the same value, increase the counter. So how many times do they overlap? Essentially 2 lists, all right? So just to warn you about that, just check the number of n. Check whether they're the same or not. If you're dealing with 2 different inputs or multiple inputs, check their size. Therefore, it's, as I say, it's not O of n squared because they'd have to be the same size. It'd have to be n times n. Here we have 2 different variables, A and B, just placeholders, yeah, whatever they are. O of A times O of B. Yeah, okay. Final point, and we'll move on. Here is, again, looking for the most descriptive term. Okay, so let's have this rather odd mix of loops. Okay, so the first one, for each element in L, and let's assume that we have 1 list this time. We're not told, but let's assume we have 1 list. Okay, so therefore read this as n for each element in list for n O of n. Okay, well that's O of n, isn't it? Because we're doing an operation n times, depends on the length of the list. Okay, so that's O of n. But then we've got this nested for loop. Remember 1 list, and read this as for each n in list. And then inside this we have a nested loop, don't we? So we've got O of n, O of n. That gives us O of n squared, O of n times O of n. Because for each n, you're also doing O of n. So therefore it's O of n squared. Loop inside a loop. I presume you've seen this before with creating like a 2D array. Because you generally have an inner loop and an outer loop. I presume you've seen something like that before. Or if you've not, just focus on one activity in one loop, and then you just repeat it. Okay? So if the inner loop is drawing a row for a table, think think of your Excel spreadsheet, you've got columns and you've got rows, haven't you? So if you can create the inner loop to do a row, so it gives you one row, then just do that multiple times. So you get the rest of the row cells as you go down, yeah? So that's what we've got going on here essentially in visual format. So O of n squared here and O of n. So out of the two, we've got two different classifications, haven't we? All right. This is a very strange example, but it's here to make a point. You generally wouldn't have this, all right? But, well, if we had to classify our overall algorithm, which one of the two would be a better fit? The second one. And why would you say that? Yeah, essentially, doesn't it? It would be a bit more dangerous to classify as O of n, this entire algorithm, because we've got a worse performing thing here. Essentially, if we're looking for the, what is the maximum this could be, the worst case, well, worst case it's going to be O of n squared. If there was a condition here that we didn't have to run this O of n squared, if we had an if statement here, only do this if something is true. If we weren't always going to do it, hey, good to see you. If we weren't going to do it every time, yeah, the best case, it could be O of n, because if we may not do this. So maybe best case, we only do it n times, O of n. Okay, but worst case, if we're trying to capture the worst case, the worst it could possibly be, well, here O of n squared takes much longer, doesn't it, as you say? So it would be better to go for something like that. We haven't got it though, we haven't got an if statement, so essentially, yes, we would side with this. That would be the average case if we had to run the nested loop. You might potentially elaborate on that. You might say, oh, well, why don't we do O of n plus O of n squared? Okay, you could do that, but remember we're looking for a single classification. That was my point earlier, wasn't it? We're trying to find one of these, remember? We're not so interested in whether it's a mix of them, whether it's one plus the other one. We do have that case happening here for linear arithmetic because it's O of n plus or times log n and log n. But remember, we're siding with one of these, aren't we? So we're going for quadratic rather than linear here. Okay. Have I overwhelmed you? Is that a bit much? But as I say, you might not get it exactly the first time. That's fine. It takes a bit of time just to get used to. We'll keep doing this, don't worry. And the idea is to train you to get better at classifying stuff. Indeed, if you have a go at the exercises today, there's a few ones to get you started. We're going to keep doing it, don't worry. Okay, we'll keep coming back to this. Don't worry, you'll see it more times. Remember, elements on the x-axis. N is here. So as n increases, the time taken will scale. Remember, asymptotic complexity. We're measuring the rate of growth, trying to classify the rate of growth in mathematical terms. Not necessarily based on time, because time's going to fluctuate. It's going to fluctuate a lot, okay, based on conditions, as we said. We're more interested in classifying theoretically here with maths terms, all right? So, it might have been a bit too much to get all in one go. Don't worry, we're going to unpack it. We're going to keep doing more of it. Let's give you something tangible. Let's give you something that you will be able to run yourselves and be able to work with, okay? So let's have a go at just timing some of these operations so we can start to get a handle on this, okay? So I'm going to import the time function, the time package, and also random, okay? So as they say, we're going to measure time, we're going to quantify it so you can get a handle on it, and then generate a load of random lists so you can see this, okay? And there's one little nuance here I need to mention about Jupyter, because remember, Jupyter caches things, doesn't it? If you remember back to your basics from level 4, you can declare variables in one cell and then use them in other cells. So it actually puts them in memory, okay? So one thing we would advise, if you're going to do this, if your first time you'll be fine, but if you've got previous data in your Jupyter notebooks, just make sure you flush out the cache. So there's a little trick here. You can use clear all outputs. If you're in VSC, it's elsewhere in Anaconda, Jupyter notebooks, but you'll find it in here. Just clear all the outputs so you get to run it afresh, okay? Because we don't want the cached memory to affect the performance and give us a different measurement, okay? That's actually something else. We'll get to that. That's memoization when we get to dynamic programming. But for now, we'll just do it from scratch so you get to see the times. Okay, right, so let's have a look at something simple. O of n. All right, so 500 elements. There's our size, 500. Okay, I'm going to create a list of that size. We could put the list cast in here as well if you want to see them individually. Okay, and then we're going to start the timer for each element, read I as n, for each n, for each number of elements in list. N will give us, n is essentially size. So for each element in size, 500, how many times are we going to call this function? I can zoom up if you need it. So if I'm writing a loop which can print every element, how many elements have I got? 500. So how many times is this loop going to run? 500. 500 calls. And remember we said that the print could be constant, essentially, because it's always going to take the same amount of time to get to element 0, to element 1, to element 2, element 3, element 4, 5, 6, 7, all the way up to 500, or 499 technically, start at 0. Okay, so it doesn't matter, it should be constant. You might get slight fluctuations based on architecture, but mathematically it's constant. Okay, call count possible. So we should expect to see 500 calls if we've got a counter. Repeat it every time, 500 times, printing out the I as we go. N time, and then we'll have a look at how long it takes to do that, and the call count. That's just counting the number of operations. Okay, just so we can get a handle on this, let's have a look at it. Here we go, here's the print register, 0, all the way down. Thankfully it's going to abbreviate for us to 499. Time taken to read 500 elements is fairly quick. That's not too bad, is it? That's less than a second to do that. 0.0007, so a tiny fraction of a second, okay? And then just to confirm to us, how many function calls did we make? 500. Okay, fairly simple, hopefully. Yeah, so every time you've printed out the contents of a list, of an array, you would have done something like this, okay? So you could classify this as what mathematical time classification? What would you classify this as? What's the rate of growth here? Anyone want to tell me? We've got a single for loop, not nested for loops. O of n, yes, it's O of n, isn't it? Yes, so the time taken is proportional to n. So if you had 50 elements, you do it 50 times. If you've got 500 elements, you do it 500 times. If you've got 5,000 elements, you do it 5,000 times. Yeah, so it's proportional to n. It depends on the size of your structure. Let's exemplify that. Let's move down to the next cell. We've got 50,000 items. Same thing, size n is 50,000. And what are we doing? For every element in list, what's the size of our list? 50,000. So how many calls do you expect to see? 50,000. Yeah, and you should see numbers 0 through 49999. Okay, same thing again. Let's time how long it takes. All right, let's do all that. Again, pretty quick. It's done it for us already. Okay, all the way down to 49999. Yeah, so it did it in under a second. It took a bit longer though, didn't it? 0.06 compared with 0.0007. I suppose we'd have to get the time of each individual print to work out. I mean, look how precise it is. It's incredibly precise, isn't it? You've got lots of floating point numbers here. So it's going to fluctuate. It depends on architecture. It also depends on how many other apps I've got running as well, by the way. And I'm recording this as I go. So I've got Panopto on the run. I've got loads of other apps, Microsoft Teams, my Outlook, email. So that's going to affect the overall performance, isn't it? Multitasking, okay, parallelization. Oh, is there a question coming in? I suppose it would, yes, because you've got a read, you've got an operation to access the memory location, and then you're going to get it out to the screen, haven't you? So you've got two operations essentially by doing this. So yes, if we were just reading, that should, in theory, be the amount of time it takes to print subtracted from the amount of time it takes to read. So yeah, you could also try that. That's true, because we have got a two-step operation. I was trying to give you something tangible, but yes, you're right. That would happen even quicker. You just wouldn't see anything, okay? You'd have to know that it's read. You can assume that it's read the 5,000. It's gone to those memory locations, looked at them all, and says, yeah, we're done. We've read them. I've understood them, okay? But just printing them out to the screen is a separate operation. And by the way, print would force the read as well. That's another thing, isn't it? I suppose I've got to tell the application to actually go and look at each of those elements, haven't I? So that's a kind of, you'd have to separate those two things, wouldn't you, technically? So potentially they're rolled into the same operation here, read and print, essentially. But yeah, if you were in C++, you had pointers, yeah, just look at the memory. You could do it that way, couldn't you, rather than print them out. Okay, so there we go, 500 to 5,000. Little bit of an increase. All right, let's push it even further. How about 5 million elements? How long does that take? 5 million elements, how many times do you expect to run the for loop? 5 million times, exactly. So how does that stack up? All still going. Here we go. 5 million elements. 5 seconds, 6 seconds, getting up to 10 seconds. Ooh, just under 10 seconds. Maybe you have to time it on yours and see how long it takes. 0 through to 4999999. Okay. Now, that took a bit longer, didn't it? It wasn't too bad. 10 seconds, 9.95 seconds. 5 million calls, function calls, okay. So are you seeing the basic principle? Time taken depends upon the size, doesn't it? I can't print 5 million elements in the same amount of time I could print 500. Kind of hopefully obvious, hopefully self-explanatory, but just quantifying it for you. The time taken to do something, number of operations you have to do depends upon what? What does it depend upon? Size, thank you. The size of the structure, that's it. There's no trick question here. Trying to show you this. O of n, let's show you here. O of n is this line here. Okay, so here we go. Imagine 5 millions here. Time, y was 10 seconds. Well, we did 500 fairly quickly, less than a second. We also did, 50,000 in less than a second. But 10 seconds took a bit longer. But we still got the O of n line, haven't we? Yeah? That's what I'm trying to demonstrate to you. Okay? Hopefully we're slowly starting to pick it up. All right? So let's, I think, have we got one more, or was that, I think that was the end of that, yeah. So something you can have a go at, something you could potentially play around with, see if you can push it a bit further. It will scale further though. And it depends what architecture you're on as well, doesn't it? It depends what chip you have, what processor you have, what graphics card you have. You'll get slightly different time counts to me, okay? Let's have a look at access. So O of 1, do you know what we said that was? 1 will never, it's not going to change. So it's constant. There we go. O of 1, it's constant. It's not O of n. N changes. It could be 50, it could be 500, 50,000, 5 million. But O of 1, always going to be the same. Always going to be constant, okay? So here we go. Let's stay with our 5 million length of our list, L, okay? And if we try to get to the very last element, 4,999,999, well, do you think that's going to take a long amount of time to do? Or have we got to iterate all the way to the end to get to it? No, because what? We've got an index position, haven't we? If it was a linked list of 5 million elements, and let's imagine it was a singly linked list with no tail pointer at the end, imagine I had to iterate all the way through to get to it. Yes, it would. Should take me 10 seconds, shouldn't it? Roughly 10 seconds. But here, because it's indexed, I should be able to get to it in the same amount of time as I would the first element. And that's what I'm going to try and demonstrate to you, okay? It took such a small amount of time, it doesn't even quantify it in terms of a decimal. It's going to give us some sort of power that we need to raise by to get to it, okay? One function call, time taken to get to it was tiny. Didn't take long at all to get to it. So that just proves to me I didn't take 10 seconds to get to it, did I? I took fraction, milliseconds, tiny nanoseconds maybe, to get to it, okay? Because it's indexed, I can go straight there, okay? Same thing for the middle of the list. Okay, yeah, one call again for 2,999,000, so the midpoint roughly of the list, or maybe that should be, well, technically a little bit over the midpoint, but you get the principle. I'd have to go to 4,999,999 to get to the midpoint out of 5 million. But yeah, again, fractional. A slight nuance here. It took slightly less time, if we could multiply that, 1 nanosecond less maybe. So there's going to be slight fluctuations. I'm not telling you it's exactly, because that depends on environment, architecture, etc. But mathematically, we could declare it constant because it's so minimal. Okay, and then 0, list element 0. Again, one function call. It took hardly a minutiae of time to do it. So does that demonstrate to you constant access, or at least fairly close to constant? Okay, without being pedantic about time, because remember, time fluctuates, and like I said, it depends on architecture. But mathematically, we're going to classify this operation as constant, yeah, because of its index nature. Okay, all right. So you've seen O of n. How many loops did we have for O and n? Very good. Okay, so to get O of n squared, well, we didn't have one, don't we? We didn't have a loop. O of n times O of n to get O of n squared. Okay, think of linear algebra. So let's do this for all. Yeah, because this is going to scale fast, remember. Let me just reference back to our graph. Let's show you this. Okay, so O of n was fairly tame. We did 5 million elements in 10 seconds reading through them. But O of n squared, that's going to scale faster, isn't it? We're going to take a lot more time to do that. So we're not going to go 5 million elements. That will take forever. We'll do much smaller, so you can tell. Let's start with 500, so you can tell. Let's go right back to our start, 500. Now, what's 500 times 500? If you didn't want to figure it out, we can do it in Python just to demonstrate to you. 200, there you go, 500 times 500, 250,000. That's a lot more than 500, isn't it? Okay, it should be the total number of operations that we have to perform to do this, because it's O of n times O of n. All right, so even if we had a list of 500 elements, we're going to expect, here's that loop inside a loop, expect the call count to be 500 times 500. Because remember, for every element of n, we're having to do another loop, aren't we? So that scales much faster. Well, we're only reading at this case, so we could be able to do that pretty fast. Because remember, 50,000 elements didn't take too long. Okay, 250,000 call count. It took 0.34 seconds, so a little bit more than our 0.0007. Okay, we did it pretty fast, but the call count was a lot more. It wasn't 500 operations, 250,000 operations that we did. Okay, so if we scale this to 5,000 of n, O of n squared is 5,000 times 5,000, we actually get 25 million. And that was a lot more than 5 million, isn't it? So this could take a bit. In fact, I think I've got a note here. Just beware, this could take up to a minute. So let's get it started. Let's get it running. There we go, it's off. But let's just demonstrate that to you again. We've got 4i in L, that's O of n, times 4i in L. So the call count, my whole environment's slowing down with this. 5,000 times 5,000. We should expect the operation count to be 25 million. Potentially my environment could crash. It crashed on Monday when I ran this. So let's just get it going. It's halfway there if it takes under a minute. Okay. But as you can see, our 5 million count took about 10 seconds, didn't it, to do? So 25 million, we're coming up for a minute. It should see in a minute. Hopefully it's going to stay with us. We're getting some output coming now. My whole environment's slowing down. It's creaking under the amount of operations I'm having to do. I think it gets to about a minute. Let's see if we do get to a minute. Hopefully it won't crash on me. Yes, 59.3 seconds to print 25 million. That's a lot, isn't it? And I don't know if it's going to show me. Is it going to blank on me? Could blank on me. It did it. We just can't see the output. I think it's blanked on me. Yeah. So there you go. Warning, if you run that cell. Yeah, I think it's crashed my VSC. So a lot of operations. Are we going to kick into action? I think my other cells are starting to appear. I've given my M1 chip a lot to do. Let me see if it comes back. But yes, take it as given, about a minute. So I hope you're getting it. I hope you're seeing. The time taken is definitely going to scale in proportion to the number of operations. Okay. Am I going to be able to continue on this? I think I might just have to reboot this notebook. Let's clear the outputs and let's just don't want to save. Yeah, let's just do a quick save and let's boot in to it again. So yeah, just be aware if you run that, but that hopefully does tell you what's going on. Am I going to be able to restart this? I think I cleared the outputs and I saved it. Let's just see if we can go back to it. Maybe I shouldn't have saved it. Maybe I should just load it in. What else? Maybe let me just close down VSC. Yeah, it's a definite warning with that. Just be aware of that. Okay, let's reopen the folder and let's see if we can boot in. Yeah, maybe I shouldn't have saved it. I should have just let it run. Let's just give it a minute. Okay, but I hope that's given you a chance to have a look, or I suppose I could just download a fresh copy from Blackboard. I've given it a lot to process. It's probably drastically increased the file size because of the amount of numbers that are being stored. I should have just cleared the output and run again. Oh, maybe it's the kernel. Let's see if we can restart the kernel. If not, I'll just get it from Blackboard for us and overwrite it so that we can see. Yeah, it's taken a little bit of time. I'll tell you what, I'll just download it fresh. Thankfully, I've given a copy of this without running that. So just be aware. I've probably scared you off from running it now, haven't I? But it does prove my point. Let me just overwrite my clogged up version of this one. How big was this? Let's have a look. Oh, it must be, maybe it's the kernel. Maybe it's the kernel then. So it didn't actually store the values. It just, let's see, yeah, let's replace that. Okay. All right. And let's open this up. Yeah, there we go. Okay. All right. So where do we get to? We've done O of n squared, which you saw was quite painful. It scaled very fast, didn't it? As you can see, not conducive to a large number of n. You can make it work for a smaller number of n. Just be aware, it scales incredibly fast. So it demonstrates my point, hopefully. Okay, let's just finish this up. I just need to run this cell so I can do the timings and random. Okay, I've also flushed the cache, so hopefully we'll get accurate timings from here on in. We've done O of n squared. Let's talk about logarithmic. Oh yeah, let me show you that example I said earlier. Hopefully you've got it by now. But just to mention, for log base 2, sometimes you see it written like that. It gives you the power of, essentially, to multiply 2 by. Think of binary. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. You get 0, 1, 2, 4, 8, etc. It just goes up and up and up, okay, to give you the binary. So if you put 8 as n into log base 2, you're going to get 3 back. There we go. There it is, 3 back. That is essentially 2 times 2 times 2, or 2 to the power of 3. Okay, and now compare that with log base 2 of 4096. That will give you 12 back, as we see there. Okay, so put 4096 log base 2, you get 12. So increase of 4,000 and what was that, 88? 4,088 to get to this. But rate of increase from 3 to 12? 9. Okay, so compare 9 increase to 4,000 increase. Pretty good going, isn't it? It's not linear, it's not proportional, because we didn't go from 4,000 there and 4,000 there. We actually went from 4,000 here to 9 increase from there to there. So it scales much slower than O of n, and definitely slower than O of n squared, which is important. Okay, so how would we code that? We could do recursion. Remember, recursion is a function that calls itself. So we could pass this in. And does anyone remember what 2 forward slashes refers to? I've got a little comment there to tell you. It's not precise division. It's floor divide. Floor divide, so point floor, round down. If it's ceiling, round up. Yeah, so 2.5 is actually rounded down. If we do floor division, it doesn't get rounded up to 3. It's rounded down to 2. Okay, so just remember that. All right, so here's just some examples to prove the point to you. There we go. Log base 2 of 8 gives you 3, and that's 2 times 2 to the power of 3. 2 times 2 times 2. Log base 2 of 16, 4. 2 times 2 times 2 times 2. Okay, we've seen 12. Oh, here we go. Here's a big increase, isn't it? So from 4,096 to, what's this, 8 million? 8 million. What's our rate of increase in our return? 10. So an increase of 8 million gives us an increase of 10. That's pretty good. That is pretty good, okay? So that's going to help us for very large numbers of n, isn't it? Really, we needed a logarithmic algorithm to work with our 25 million, didn't we? That would have helped us out a lot quicker. We'd have done that in fractions of a second because of how that algorithm's coded, okay? But the only thing is, it has very particular conditions to run logarithmic algorithms, okay? And you'll see this when we get to things like logarithmic search, or binary search, as it's otherwise known. You might have a binary search tree that's sorted into order. There's a particular state it has to be in to achieve logarithmic search. Okay, you'll see that in the afternoon session, so come back for that, all right? A little teaser for that, all right? Let's just finish up with this. Linear arithmetic, okay, that's O of n times log n. Okay, so multiply the two together. That's essentially the basis of merge sorts. So remember, that's not too bad. That's kind of in between both of those two things, isn't it? That we looked at, that we saw the really fast rate of increase, fast rate of growth for O of n squared. O of n log n sits in between those two, doesn't it? So there's O of n squared. O of n log n sits in between those two. It is O of n times O of log n. Okay, so let's just quickly run that for you. This is merge sort. You're going to see this in the afternoon session when we look at O6. Okay, so merge sorts allows us to essentially divide and conquer. That's one of the principles of logarithmic search. We're going to apply that principle to be able to merge things back into order. If we're trying to sort something, the basic principle is we could do 2n minus 1. So the call count for an array, unsorted array of 500 elements, should give us a call count of 2 times n, 2 times 500,000, minus 1, 999, okay? And then it scales from there in terms of the number of call counts for that. All right, and it should allow us to do things in a much faster time. That's the bottom line, okay? As we see here, 50,000 elements, call counts, size is that. Oh, here it is, let's do the merge. Here's an example of merge sorts. We'll unpack it in the afternoon session, okay? Call counts, let's have a look at this. Function calls, 999, but to sort an unsorted array of 50,000 took 0.14 seconds. Can I do this for a much, maybe we will do this for a much bigger array. We definitely will do this for a much bigger array in the afternoon. The principle being less time, okay? So it does it much more efficiently because of how it's coded. All right. These are the worst ones. You don't want to try and avoid these, but just to show you what they are. Okay, so the Fibonacci sequence, if you're familiar with this, it's there's a formula for it. What is it? I think it's O of n equal, F of n, not O of n, F of n equals F of n minus 1 plus F of n minus 2. I think it's that for the base cases. So there we go. Yeah, F of n minus 1 plus F of n minus 2. There it is. To calculate Fibonacci. So essentially, future sequences depend on previous sequences. This is a recursion principle there. If we applied the call count to this, essentially what it maps to is O of 2 to the power of n. So remember, as n increases, that's going to scale very fast. 2 times 2 is 4. 2 times 2 times 2 is 8. Remember, the rate of increase is going to grow through the roof. All right, so let's run this for n of 10, n of 20, n of 30, and see how long it takes to do. And notice how that call count increases very rapidly. So from 10 of 177 calls through to 30, 2,714,605 calls. So that's massive growth, isn't it? Huge growth and huge amount of time as it goes on from there, just to calculate these numbers, okay? It's elegant, I will say. It is an elegant solution. It's not the most efficient. Recursion is very elegant, I will tell you that, because it's the same pattern. Just repeat it, call yourself. Just be aware that grows tremendously. We'll see a solution to this in one of the later lectures, a little teaser for what's coming down the line. But for now, just introducing it to you just so you get it, okay? And then, factorial, yeah, you definitely want to avoid this one because it's essentially brute force. If it's a travelling salesman point or BOGO sort, it's even worse. You're essentially trying all the possible permutations, all the different combinations you could have, brute force it until you find the right one. So that's a very small case for a root, if you're trying to find the optimal root between a matrix. But BOGO sort, essentially, take an unsorted list. In fact, that's even worse. That's n plus 1 to the factorial. That is, try every possible combination you can think of at random. So just randomly throw out combinations of lists and hope it's the right one. That's essentially what's going on here. So sorted, this is an array of 5 elements. It took 211 attempts to get it into that state because it's all random. It's just throw out a random combination of the list, hoping it's the right one. So, that was very good. 2, number of attempts to get it to there. 7, 16, it's always going to be random, okay? Keep running it, it's always going to give you a random assortment. So really not optimal. It's just a random hope for the best, okay? Sometimes you get lucky, sometimes you don't, okay? Good for generating random things, but not so good for optimization. Okay, so we'll come into line, guys. We need to finish up. All right, so in principle, we've talked about a number of different things here, and hopefully we've started the journey. Don't worry if you're still a bit stuck. It's a process. You'll get to do it. Don't worry. Just practice. The more times you do it, the more familiar you'll get. Okay. Here's a little emoji. Oh, here's something fun to finish with. There we go. So best case omega time. That's big omega. That's our little horseshoe. That's to the moon. Taking off. Yeah. Worst case, shocked emoji, big O. Okay, but that's usually what you see we measure things as. The worst case, it could be this. Okay, and then theta, kind of average case, kind of whether it's always going to be the same time every time. Okay, so in principle, that's what we've looked at. And your questions for today are trying to get you to look at code and work out which one of these classifications it is. Okay, so keep coming back to this. You'll probably see it everywhere. It's this graph that visualizes these terms. We want to get you to start to classify your code so you get better at working out how it's evaluated. Okay, so I think I'll finish there. Any questions on that, guys? I appreciate it's quite a lot of information I've thrown at you, so maybe get a bit of time, process it, distill it. You might need a break maybe, so I've thrown a lot at you. I need to sign a load of you in as well, don't I? So let's do that. Okay. So I'll leave you to have a go at the questions if you want to, and I'll wrap up the recording. Oh wow, that was a long